biomedicine, and we're going to be specifically talking about mammography and radiology, hopefully to do a couple of examples to see that some of the research that you guys are doing does transcend into being something that's very applicative and very useful to society in general. There are 5 professors working on this project. It's a National Science Foundation funded project through the Department of Mathematical Sciences and Bioengineering.
Essentially, what we just showed you was that biomedical imaging encompasses all these different types of imaging. So when people think of biomedical imaging, they don't just think of you go and get an X-ray in your hand and then it shows your head, which is probably. And so, but pretty much there's just a breakdown. And so X-ray imaging, you have just the conventional, which is just the actual picture of the basically, math is the thing that is generating these images, and math is what's behind it. So if you know math, then you sort of
The other big thing is when we went there, like Dillon said, it was, well, how do you generate this image? And it was a lot of, I do it, I push a button and it happens. So there's some magic that happens between pushing that button and getting that image. And what we like to think of is that's the math. And one of a really good example, specifically for the radiology and mammography application that we're going to talk about, is the radiologist doesn't just offhand memorize all of these different functions and ways to position the patient and everything. They have to think about the spatial relations, how the CT scanning technician has to think about, well, if I position the patient this way, what geometry has to be used to actually get a good picture? If I apply this much radiation, how long can I expose the patient for it to be safe and effective, but also get a good image? So being a radiologist or a radiologist, like a technician, you don't just push a button and it happens. You do have to know the math somewhat behind it to get that good image. And they're stacked crates, and so you can't see inside of them. All you can see is that basically maybe the bottlenecks, right to where it would probably be filled or not filled. There's three options for the containers. One is that it's completely empty. One is that it contains milk, and one is that it contains juice. The question that we want to know is which type of bottle is in which compartment. So we want to know, is it empty, does it have milk, or does it contain juice? The idea is that milk is 3 units, juice is 2 units, and empty is 1 unit. This is an additive process. So as you go across, if you put a number 1, 3, and 2 here, you're going to have an additive across of 6. So it's basically like a Sudoku problem, but you have to make the numbers line up to add columns and rows. So there are 2 different solutions actually, and ironically it's half and half on who figured out what. So the purpose of this exercise is to show you that it's important to know enough information to make sure that the situation that you're given is clearly understood. What else could I have told you for this activity that would have made one of your answers right? Because if I asked you now, which answer is correct?
First one.
Either one, right? So what information for this activity could I have given you that made it, so that we could actually determine which answer would have been the right one? How could I have changed this activity? A third dimension, like what?
Z-axis.
The z-axis, or diagonal. So if I told you that the diagonal had to be 3 up there in the corner, you could have gotten it, right? At the same time. You also raised a good point, though, that you could have swapped some of your columns maybe and still have worked.
Like in this case, if you were to shine a light through the bottle, I guess what was actually inside the bottle would determine how much light you get through. So obviously, if you had milk, that would be a pretty thick liquid versus air, which is not very thick. And so essentially, that's what this picture is showing you. Is just that the amount of radiation that you have flowing into a certain tissue is going to depend on what's actually inside the tissue as to how much radiation comes out. And so pretty much we end up having this data about the boundary of what's on the outside. So that amorphous blob over there, you can sort of see what the boundaries of it are. And so what's actually inside it is determining the radiation that's going to go through and then be detected by your detector. So obviously one way would be to add more detectors. So obviously in this case you only have one detector where you have one X-ray source, and then those are hitting the detector from only one angle. And then in case number 2, you you have two different X-ray sources that are intersecting, and then they're meeting at two different detectors. So basically what you're doing is you're adding more data in, and so you'll be able to get more specific answers to the problem.
And the other big thing that's kind of apparent if you look at the picture is, as Dr. Khan explained to us, if you notice on these three, you're only actually getting the object that you want to see with two rays. So you're not even getting really any information off of this one. But these, you can see that you have more kind of area covered, which is going to give you that better picture as well. Some of the pros of mammography is that early detection does equal earlier treatment, and generally that can be better for the patient and reduce the number of deaths. Some of the cons that we've spoken about before is that you have that repeated exposure to radiation, and then this is often why they have you start later, and women start later in their life when they're doing mammograms simply because of that exposure. You also might have false results, and therefore either overdiagnose or overtreat what's there, which again, if you're overdiagnosing or overtreating it, that continued exposure to radiation is not good for the patient. So here's an example of a false positive test. What this shows is, in this A, they see there's a possible mass. This is done with a 2D mammography application, and so initially when they did this, they would say there's possibly, yes, this woman possibly has cancer. But in reality, when they did further studies with what was called 3D mammography, you can see that in B, C, and D, you don't see that mass. So it's considered to be a false positive test, which is kind of nerve-wracking for the patient themselves, because here they are presented with, you might have cancer, and in reality, it was just kind of just on the first image that you saw. On the flip side, you can have false negative.
So pretty much the exact opposite of that situation is if you actually do have a tumor, and then you get imaged, and then the image doesn't really produce a clear picture of you actually having a tumor, it's pretty easy for the radiologist to say, well, that's just enough massive cells, or that's just some benign object within the actual tissue. And so essentially, this is a 2D mammography image of a breast, and then so it sort of shows a little region where there could be something, but then obviously the radiologist did not think there's a tumor. And then with the 3D or the tomosynthesis image, you can actually see more clearly that there is a tumor. And so essentially the 2D, when the tumor was hidden, I guess in a way, and you did not see it, that was bad. And then they upgraded it to the 3D, you could actually see that, okay, well, I guess the tumor.
Applications being biomedical imaging. And then here are some quick bullets as a backup for why what we say is true.
So therefore, what usually happens is that you take slices of the images. So you take whatever object you're trying to image, you take various slices, and then you have to put them together, the information together into a three-dimensional structure. But even two-dimensional structure is really one-dimensional rays. So even then, we talked about the region of interest and then we have the rays. So from the rays, you have to go back and see how much information you can get. So the more rays, the better. Why X-ray goes in a straight line? You're right. Some near-infrared radiation, the sunlight does not go in a straight line. It goes into our body, gets scattered, so the imaging gets very complicated. That's the research I do. But X-rays are much stronger. They're more high energy. So therefore, they goes in a straight line. So you know exactly the ray that's going in, you know where to detect.